Hello, wonderful people. Welcome to Cosmology Talks. Today we have something I'm very excited about. The thing about the SH tension is that each individual local probe is sort of in a bit of tension with Planck, but not enough to get excited about on its own. But the interesting thing is that nearly all the probes are on the same side. So the naive thing to ask, which I've certainly asked over and over again, is why not just combine the data and the methods to measure S8? To which we always get the answer, it's not that easy. But today is the cosmology community's lucky day because we have a combined cosmological analysis of both the dark energy survey and the kilo-degree survey cosmic shear with the ultimate combined cosmology constraints. With us today we have Alex Amon, who's a Kavli Fellow at Cambridge, Marika Asghari, who is a lecturer at Hull University, Ami Choi, who is a research astrophysicist at the NASA Goddard Space Flight Center, Anna Poradon, who is a postdoctoral researcher at the University of Edinburgh, and Simon Samaroff, who's a postdoctoral researcher at Northeastern University. So yeah, two things I'm very excited to hear about are obviously the ultimate combined constraints and what the tension is, and given that where we go next, but also were there fears about the difficulty to combine these measurements valid, or did it turn out to not be that bad? And if it did turn out to be that bad, like what specifically were the problems that they were facing? So yes, welcome dark energy survey people and kilo-degree survey people. Do you want to start by telling us briefly about the work?
So we carried out a joint cosmological analysis of cosmic shear from the kilo-degree survey and the dark energy survey. And the six of us teamed up to combine these two surveys, and our teams spanned both collaborations. And this was really important. So we had this incredibly valuable learning experience to disentangle what our teams had done together. And we had plenty of support and guidance within the collaborations from the people listed here. And of course, our work builds off of an enormous effort from each collaboration to deliver the calibrated weak lensing data.
All right, so we'll be talking about data taken by surveys that were specifically designed for weak lensing measurements. And the first is the kilo-degree survey, or KiDS, which covers 1,000 square degrees and 9 filters spanning optical and near-infrared wavelengths. And we'll refer to the latest data release as KiDS 1000. So that's in this kind of yellow-orange color here. Now, we are also going to be talking about the dark energy survey, or DES, which covers 5,000 square degrees and uses 3 optical filters for the lensing measurements. And the latest data release is based on the first 3 years of observations, and we'll refer to it as DES Y3. And the main results here focus on a joint measurement of KiDS 1000 and DES Y3, but I do want to point out that the Hyper-C PrimeCam survey has recently put out their year 3 analysis, and we'll show a comparison later on. So HSC is in kind of purple there, and then DES is in the big green footprint.
So with that introduced, I guess the next question is, what do we mean when we talk about cosmic shear? The basic idea is this. When we observe with our surveys distant galaxies on the sky, we see these images, but the photons that make up these images have had to travel a long way through the universe to get to us. And that universe, of course, is not empty. It contains dark matter, and the dark matter has structure. You basically have this density field between the galaxies and us, which fluctuates and has like peaks and troughs. So as our photons from these galaxies travel through that universe, they get subtly distorted and bent. Their trajectories are deflected by lensing due to this intervening structure. And you can see that in an exaggerated way in this cartoon diagram. You have our background galaxies, which are circular, and by the time they reach us in the foreground, they've been sheared into these elliptical shapes. And of course, in practice, this effect, due to cosmological structure, is far more subtle than we can see here, to the extent that you can't actually detect cosmic shear at the level of individual galaxies. So what we have to do is to take millions and millions of galaxies from these large galaxy surveys and combine them. We correlate pairs of galaxies over a large area, and that basically beats down the noise and isolates this pure lensing signal from which we can extract cosmological information. And it's at this 2-point level that cosmic shear really comes into its own as a powerful probe.
So at the end of the day, when we do a cosmological analysis, the thing that we are interested in is constraints on cosmological parameters. With cosmic shear, we normally see this kind of degeneracy between sigma 8 and omega matter, which is normally called the cosmic banana, and hence the banana here.
You've even got the 1 sigma and 2 sigma bands on it.
That was fortunate, actually. Yeah, so as you know, a banana is generally longer than it's wide. So we can't really say anything individually about omega m and sigma 8, but we can say something about their combination, which is called S8. And the combination is written here. And basically what it's telling us is where along the width of the banana we are. And the reason we see this kind of degeneracy is because with cosmic shear alone, the signal that we get from a universe that has a lot of matter, but this matter is weakly clustered, is very similar to the signal from another universe that has a little bit of matter, but that matter is highly clustered.
Awesome. Enough of the suspense then. Let's get into the results. What we'll do for the viewer is we'll have a look at the actual results of this combined analysis, and then the speakers will give their thoughts on what was interesting about this, what was still confusing, what they're keeping them up at night even now, and then we'll go into the details about exactly how the things were combined. But yeah, enough from me. Let's get into the results.
Yeah, so finally you can see here the results of this combined KiDS plus DS cosmic shear analysis in pink, and these results on sigma 8 and omega m and S8, as Marika introduced just recently, are compared to the same results obtained from early universe observations from Planck in blue, and also with the individual results from KiDS 1000 and DSY3 in orange and green respectively. So as mentioned at the beginning, part of the motivation for this work is the fact that all these weak lensing observations tend to favor lower values of S8 compared to Planck. As you can see here, when combining the measurements from both KiDS and DS, we still find a value that is lower than Planck at the level of 1.7 sigma. So in this table, you can see the actual constraints on S8 for each one of these cases, the SY3, KiDS 1000, and the combination. And we estimate that the difference with respect to Planck in S8 is about a level of 1.7 sigma. And also we find the same difference in the 2D plane of S8 and omega m, which corresponds to the right panel.
A few things here jump out to me. I mean, I guess the tension or lack of tension in DES has been boosted up a bit, and the tension in KiDS has been dropped down a bit, I guess. But yeah, what is it that you find curious and interesting about this state of play now?
One insight is that KiDS and DES take pretty different approaches for their analysis choices. So each team originally presents well-reasoned arguments for their choice, but we do arrive at different choices in our fiducial analyses. And so for the joint analysis with the statistical power of both of the data sets, neither of our pipelines, neither of our analysis choices were sufficient. And what we found was that when we were trying to come up with our hybrid pipeline with a new set of analysis choices that would work for this combined statistical power, some of the analysis choices are very easy to converge on because they have tests that you can do that clearly identify a more correct model or two. But other choices, other model choices, the reality is that there's just not yet concrete evidence to select one approach over another. And for those systematics, we needed to do a bunch of tests and reason out a choice. And we do that, but it is harder to get convergence on what's the correct model.
Is the problem at the level of the actual infrastructure that the telescopes are different, or is it just in method techniques that have been chosen at the data analysis stage? Or is this something that will become more apparent in the future slides?
Yeah.
So on the cosmological side, is there anything here that you find particularly interesting and want to note as a group, or as an individual if you disagree with the rest of the group?
So I can add something that connects to what Alex said. So to do with the modeling choices that it wasn't obvious what to do. Now this plot doesn't show that, but we're going to show it later. One of these cases was modeling of intrinsic alignments. We're going to go into a little bit more in detail later. So we find that the two surveys made different choices, and if we analyze our data with these different choices, we get quite different results. And that's something that was probably the most surprising result for me, or the most interesting result. I wouldn't say I lose sleep on it, but it was definitely the most interesting result for me.
And all five of you are happy with these pink contours, and or has there been like internal disagreement that some of you would like something else to have been your final fiducial decision?
After more than 1.5 years of mock analysis, we are pretty confident about the results we have, as we will show later, and the readers can also see in the many appendices of the paper, we ran dozens of mock analyses to understand all the different analysis choices, and we are very confident about these results.
I think the mock analyses are where we really understood where individual pieces of the model, like which ones were important for causing different shifts and in what direction. And there are a lot of pieces here where we simply don't have a very well-motivated way of choosing, a particular element of the model. So that's something for the future.
One thing that I find very curious that I would like to know about is, I guess, this is literally just cosmic shear, but since the KiDS 1000 data came out, since the DES Year 3 data came out. I mean, some of the people here have even given cosmology talks on what I'm about to say, but you've done other analyses, these like 3x2 point things where you've added in spectroscopic galaxy surveys and things. I guess I'm just being annoying and I'm pushing the bar. You've now combined KiDS and DES for cosmic shear. When can we wait for the KiDS plus DES 3x2 point analysis, now that you've got this pipeline to do KiDS and DES at the same time? How difficult is it now to take that next step?
It's actually even more difficult because of the additional model parameters that come in. So the 3x2 point, a big thing is that it depends a lot on galaxy bias, for example, which is another parameter which can be an astrophysical systematic, where it can be very complicated to interpret that and to also make sure that the different surveys have consistent procedures for dealing with that galaxy-galaxy lensing part and the galaxy clustering part. That's actually a whole nother layer of complication that we did actually, as a group, think about doing that with our analysis, and then we decided it was a little bit too much of a mouthful at once.
And is it in the pipeline, or is it, have you now got DES Year 6, KiDS Legacy, and other things that are taking priority?
Yeah, I would say the latter. KiDS Legacy and Y6 are sort of the immediate priorities. But you might see from other surveys, so LSST Dusk has also been doing some reanalyses. I think that could also be a good venue because that's a natural environment where a lot of the people from KiDS and DES and HSC are already coexisting in a broader collaboration. So it makes a lot of sense also to do some of these studies there.
If people are remembering this talk and this paper 6 months from now and there's only two things they remember, what do you want them to be? And then we can move on to the actual nitty-gritty details about how you did this analysis so that we can have a more informed discussion about why is it exactly that intrinsic alignments are shifting things and that sort of thing.
I can start off with the first one. So the first one is that it's important to make your analysis choices consistent before combining results from separate analyses. And some of the evidence will show later on in this talk.
And the second takeaway for us is that it's very important to understand the impact of analysis choices, as they can have an impact of up to half a sigma shift. And if they add up, they can become even more significant at the increased statistical power of KiDS plus DS. And so we're going to talk more about this later.
All right, let's now get into more details about the analysis. I guess starting with the background, can we go into more details about what the dark energy survey is, what KiDS is, and how one analyzes that data to get these contours at the end?
Let's go into more details on DES Y3, KiDS 1000, and HSC Y3. They are highly complementary. So you can see that they cover different regions of the sky, although there is some overlap, which is actually good because then you can do some other sorts of consistency checks. But if you look at this table here, that gives some comparison between some of the main attributes of these three different surveys. So for example, DES Y3 has the largest area, KiDS has a slightly smaller area, and HSC has the smallest area. But then HSC and KiDS both have more effective galaxies per square arc minute, and HSC in particular has really excellent resolution. So these are all complementary in terms of these attributes. And also to point out, KiDS 1000 has coverage in 9 bands spanning the optical and near infrared, and that can be really helpful for some of the ingredients going into our analysis. The last thing to mention is the choice of statistic which is used. So DES Y3 uses the real space 2-point correlation function, so that's known as psi plus minus. So HSC also uses psi plus minus, but also Fourier space CLs. And then KiDS does measurements in both psi plus and psi minus and CLs, but their main statistic of choice is Kosebe's, which is particular compression of the psi plus minus signal, which is also important as an optimal way of separating the E mode signal, or the real cosmological signal, from the B mode signal, or what corresponds for a lensing analysis to systematics.
I think Marika gave a cosmology talk a few years ago on Kosebe's.
All right, so this is a slide that combines all of the as-published results from the 3 different surveys. The as-published part is important here because what we're showing later is really trying to make sure that the choices and the setup is all consistent with each other. But here, this is using the survey's official or their fiducial pipeline and how they want to configure everything. And there are some differences in later on when you see results from our paper. But you can see that the 3 different surveys, lensing surveys at the top, they all have relatively consistent data points and error bars. And they're all, interestingly, on the left side, so they have a lower value of S8 compared to the Planck 2018 published version.
You kind of implicitly said what I'm about to say explicitly, but in the contours when you showed the results, the DES stuff was exactly or almost exactly 1 sigma away from the Planck, whereas here it's clearly more. I guess that's the point you were making, Amy, that in your newer analysis now, you've updated some of the DES pipeline. So that seems like an interesting thing to flag up, that whatever decisions you've made in this analysis have actually reduced the tension between DES and Planck. So, I mean, if we're telling stories in the future about what resolved the S8 tension and it turns out to be systematics, it feels like this might have been one of the crucial steps, that your analysis has realized some of the things that were wrong that were causing the tension. I mean, okay, if it turns out to be new physics, that'll be a completely different story and this will just be some random systematic that got fixed. But do you know kind of more or less what it was that has shifted DES up by what looks like almost a whole sigma?
We're going to go into this in later slides.
That's a good answer. We can be patient. Be patient.
When we think about these shifts, we don't really think about them as fixing what the original survey results did, because I think those choices were all made for very good reasons. And it's not really that there's anything wrong that got fixed, really. It's kind of understanding where these shifts or different choices that you do when you get a more statistically constraining data vector, that maybe it comes out a little bit differently. I'll just say quickly, all of these data points relative to Planck, they're somewhere between 2 to 3 sigma different from Planck. It's up to you whether you care about that as a tension or whether you consider that actually to be relatively consistent. Here we wanted to give an overview of the process going from the input images to the output cosmological parameters, and also talk about which part in particular we focused on in our work, since there are many elements that took whole teams of people years to create. And so first of all, it's really important to acknowledge the work that's been done by everybody who worked on collecting the data, reducing the data, calibrating it, and then putting together catalogs of calibrated shapes and calibrated redshift distributions. So for cosmic shear analyses, really the shapes and the redshifts are 2 of the most important ingredients that go into the cosmic shear measurement. What we're doing in our work is to not try to fiddle with those earlier pieces with the calibrated shapes and redshifts and assume that each survey did the best job that they could on those ingredients. The calibrated shapes, redshift distributions, and images, those are in a different color, slightly orange color, because those are pieces that we did not address in our paper. We didn't change. And then the things mostly to the right, the boxes are in pink as pieces that we did consider in our analysis. And that one that says measurements and covariance, which is a little bit on the orange side, that's kind of the transition area, because we didn't change some aspects of the measurements and covariance in the sense that we did the same methods that the different surveys were using. So COSABIs for KiDS and psi plus psi minus for DES. And also an analytical covariance for both of them using the standard or the fiducial approaches. But we did redo the measurements for the joint data vector because if you remember from the other slide, there is a bit of overlap, about 400 square degrees between KiDS and DES. So in order to properly do the data vector, we excised the KiDS area from the DES footprint and redid the measurement for psi plus psi minus. And we also recalculated the covariance, the analytical covariance corresponding to that slightly smaller DES footprint.
As a complete outsider to this, it just seems a little arbitrary, this pink versus yellow distinction. Why should we just trust that the calibrated shapes, even though they were done differently, is totally fine to not have to reanalyze? Is there a clear way to make a naive outsider understand that?
It's a purely practical reason. I mentioned, for example, it took maybe 50 people 3 years to do some of these boxes for DES and KiDS, and it is a very difficult exercise. So to kind of redo that or readdress it would probably take many more work years of effort from more people. And so I think it's a really great exercise to do in the future. And certainly we're not saying this distinction means that people should fully trust everything going on the left side of this flowchart. It's more a practical trying to create a project that was tractable.
So there is another distinction between them. So the yellow stuff can be specific to the survey a little bit as well, because they have different specifications, as you saw in one of the slides. Some methods might work for one while it doesn't work for the other. So we can't harmonize everything for the yellow, but we can do that for the pink. And that was another reason we were mainly focusing on the pink.
But I totally agree with what Ami said, that that's kind of the next step that we should be doing ahead of the Roman Euclid era to try and untangle, can we homogenize our calibration methods?
The rest of the pink part is really the topic of some of this paper. There are different things you can do as you set up your model and the analysis. So for example, that top box talks about scale selection, nuisance parameters, prior choices, and then those are different choices of either the model in particular or maybe how you're doing the analysis with a given model. And those models kind of cover in general the three things that are listed there: nonlinear power spectrum, baryon feedback, intrinsic alignments. The reason that those three things are listed in particular is because they are some of the most important aspects of the model, or at least we found this. And then all of this gets put together with the measurements and then goes into a likelihood. And then there's also a choice of how you can sample from that likelihood. And that's something that we'll also talk about briefly later. And then finally, when you put all of these pieces together, that's when you get the output parameters with some sort of error bars on things like omega m versus S8. All right, we are now going to go into specifics of the model and the analysis. And first, I'll say that the model that we're considering here is the flat lambda cold dark matter model, or LCDM for short. And the main 6 cosmological parameters are shown here in the top, along with the prior ranges used by DES Y3 for the first column and KiDS 1000 for the second column. And it might be kind of hard to quickly look at these, but I'll say some of them are fairly comparable with slightly different prior ranges used. But there are 2 main differences that I'll highlight. One is that DES marginalizes over this parameter called A sub s. This is the amplitude of the primordial power spectrum of scalar density fluctuations. Because AS remains largely unconstrained on its own, the choice of priors here does directly impact the posteriors. So KiDS chooses to mitigate the sensitivity to the choice of priors and to also simplify the parameter volume, which you can see an example of in the plot to the lower right, which is taken from one of the KiDS 1000 papers led by Benjamin Yokimi. This is a plot I'm showing for parameter volume reasons, but also to point out that each of the parameters that has a panel here, so it's omega matter, so the matter density in the lower left, little sigma 8 next to it, and then also S8, which is a combination of omega matter and sigma 8 in the y-axis in the left. These are all highly correlated parameters. So it's really a choice which one you decide to marginalize over, but you do have to be careful about the choice of the prior range and explore one that is appropriate so that it doesn't make a big difference for the posterior. KiDS made the choice of marginalizing over S8, and DES marginalizes over A sub s.
I'm a little confused by this plot. What is the blue curve and what is the red curve?
This plot shows for some of the parameters that are correlated what happens when you sample over a prior of A sub s. And for comparison, what's shown is from the dark energy survey year 1 analysis by Troxel et al. From several years back, what those contours from the data look like.
If I can say, maybe try and just repeat what you've been saying in my own understanding. The red lines here in this plot have no data in them, and it is, if you take the A sub s prior and then convolve it into what that would look like in an omega matter space, this is what it looks like. Whereas the blue plots are then when you add the data and say, now what does the data actually say with this prior? So the message is kind of that the data is within the prior range, but that the prior range isn't some nice Gaussian.
That's right. Yeah, there are tails in the distribution. And so if you're not careful with the prior for the data, your prior could end up being too informative. And then the other main thing to mention here is that we have different approaches toward neutrinos. So in their fiducial setup, KiDS assume massive standard model neutrinos, assuming the normal hierarchy at the minimum sum of masses. And this is 0.06 electron volts. Whereas because we haven't experimentally measured this quantity yet, DES chooses to be agnostic about that. So it is not fixed in the DES analysis.
The next analysis choice that we had to think carefully about for this were intrinsic alignments. And intrinsic alignments are one of the major systematics in cosmic shear. The little cartoon diagram at the bottom here is meant to show what intrinsic alignments are in a nutshell. So essentially you have your observer on the left, you have this dark matter over density in the middle, this blue blob, and then you have some galaxies around it. And galaxies in the background, far away, they're lensed by this overdensity, so you get a cosmic shear signal from correlating those galaxies, and that's what we refer to as GG here in this diagram. But you also get these additional correlations which come from the fact that galaxies which are local to this overdensity interact with it. So galaxy shapes are locally distorted, they point towards this mass, and that can induce correlations. We refer to them here as GG and II correlations, which can kind of mimic cosmic shear. And if you don't properly model them, that can be turned into a bias in your inference when you try and work out cosmological parameters. And KiDS and DES took slightly different approaches to modeling this effect. KiDS used something which has been widely used in the literature before, this nonlinear alignment model, where you basically assume a fixed scale dependence for these two additional correlations, these GI and II signals, and you have this free amplitude which basically just scales the magnitude of the effect up and down. Whereas DES, we use something called the tidal alignment tidal talking model, which is basically the same but a superset of the NLA space. So you include additional higher order terms with associated free parameters, which basically just make the intrinsic alignment signal a bit more flexible, so you can accommodate in terms of shape and redshift dependence. We marginalize over these parameters in both cases with basic uninformative priors over a fairly wide range.
Okay, so our observables are 2-point statistics of the shear field. In order to model them, we need to have matter power spectrum. So in this plot here, you can see the linear matter power spectrum that's shown in black, and two nonlinear matter power spectrum that are shown in red and blue. We have halo fit, that was the choice for DS, and then we have HM code 2016, that's what KiDS used. So when you do a cosmic shear analysis, the scales that you're mostly sensitive to are around where this shaded region orangey part is. Exactly where it is, it will depend on what kind of scale cuts you have, what redshifts you're looking at, and so on. But as you can already see here, when you compare the linear power with the nonlinear power, when you're in this shaded region, you're in the quasi-linear to fully nonlinear region. So in order to do our analysis, we have to have a nonlinear power code. Now, KiDS and DES chose different codes to use, and each of them did their own tests based on their own criteria, and they deemed these methods to be sufficiently accurate for their analysis. Now, when we combine the two data, our statistical power increases, so we had to check this again, and then we'll get to this later. Now, the thing is, these two, as you can see in this plot, they look like almost they're the same. And they are actually very similar. The result they give you is very similar, although the methodology is different. But the small differences, as we'll see later, will matter.
Another analysis choice that we have to worry about is how to mitigate the baryonic feedback effects. So as Marika showed, we're really sensitive to nonlinear information with weak lensing. So we have to model not just the nonlinear matter power spectrum, but the impact of baryons, which tend to suppress the matter power spectrum. And the problem with this is that there's really this large scatter in the predicted amplitude and extent of the baryonic effects from simulation. So that's what we're trying to demonstrate there in the plot in the bottom. I haven't labeled which hydro simulation is which, but you can already see that there's a large extent and there's a lot of uncertainty in modeling this effect. So weak lensing surveys have two options, and KiDS and DES took different approaches here. You can either discard the measurements on the scales that are sensitive to these effects, so that's the approach that the DES takes, or you can attempt to model the feedback with some parameter and prior range that captures the uncertainty spanned by these simulations, and that's the approach that KiDS took.
Looking at this plot super naively, in order to make a scale cut that you're not sensitive at all, it feels like you have to go off this plot almost.
Yeah, so the way that DES does their scale cuts is this very intricate process where they remove scales in every bin pair until the level of bias is below some tolerated threshold that we choose.
Now, the last difference in analysis choices between DS and KiDS is the sampling algorithm. So in order to obtain the contours and the parameters that we showed before, we need to estimate the posterior distributions on the parameters. And in order to do that, we need to sample the likelihood at multiple values of the cosmological parameters within the regions allowed by the priors, which are shown here by these square brackets. And so there are different sampling algorithms to do that. DS and KiDS both use nested sampler algorithms, which characterized by starting at the edges of the priors and then moving inwards to regions of higher likelihood. But the algorithms themselves are different. So DS use polychord and KiDS use multinest, and we're going to talk a bit more about the impact of this analysis choice later.
Okay, thanks for all the background on KiDS and DES and possible systematics and possible different analysis things. So let's maybe get into now how you chose between these various possible analysis methods that DES and KiDS were doing, whether you thought DES was doing it right or KiDS was doing it right in each step, or you made some hybrid choice, and what ways it pushes the various cosmological parameters when you're making those decisions.
As we have seen, there are multiple differences in the analysis choices that each collaboration took. And given the increased statistical power of the joint KiDS plus DS data vector, we needed to revisit if these analysis choices were still robust to this increase in statistical power. And therefore, we ran dozens of mock analyses on joint KiDS plus DS data vectors. So we generated these data vectors by generating theoretical predictions, assuming some analysis choices and particular values of the cosmological parameters, and then we analyzed those data vectors with both the KiDS and DS pipelines and also variations of those pipelines. And we found that the two things that caused the highest impact at this statistical level of KiDS plus DS were the nonlinear modeling and the intrinsic alignment modeling. And so, for example, here, when we considered a joint data vector generated with HM code and TAT, which combines the KiDS choice for the nonlinear modeling and the DS choice for the intrinsic alignment model, and we analyzed that with either the KiDS pipeline or the DS pipeline, we found shifts on S8 going in opposite directions. So when analyzing that joint data vector with the KiDS pipeline, what we're doing is testing the impact of the intrinsic alignment modeling, because KiDS uses HM code as well. And so when analyzing among data vectors generated with that with a simpler intrinsic alignment model, which is NLA with just one parameter, we found shifts to higher values of S8. And on the other hand, when analyzing this joint data vector with the DS pipeline, and so here we're testing the impact of the nonlinear modeling, as we're analyzing data vectors generated with HM code, assuming some baryonic feedback with a pipeline that uses halo fit and scale cuts and no baryonic feedback modeling, we found that the obtained set value shifted to the opposite direction, so shifted to lower values. And so what was concerning and surprising here was that the increased statistical power of KiDS plus DS, these differences could amount to 2 sigma when comparing the results from the two pipelines, depending on the input mock choices. And so given this result, we found that we need a hybrid pipeline to analyze the results in order to have robust constraints on S8 at this increased statistical power.
Yeah, this is an interesting thought. It's a lot to digest. Maybe you can pause it and have a think.
So what is the hybrid pipeline that we use for the future results? For the cosmological parameters, our mock tests told us that these choices have minimal impact, as the prior range are wider enough that they don't matter, they are not informative. And so we decided to keep the neutrino mass free and marginalize over S8, which is a middle ground between the choices of DS and KiDS. For the intrinsic alignments, we also opted for a middle ground. So intrinsic alignments, we know that they have a redshift dependence. So we added an extra parameter for NLA, which takes into account this redshift dependence, but we didn't find sufficient evidence to justify using that, which marginalizes over 5 parameters. And so we decided to use this intermediate option of just 2 free parameters using the nonlinear alignment model. For the nonlinear matter power spectrum model, we revisited all the scale cut and validation of the nonlinear modeling against the Euclid emulator 2, which is an emulator of the parameter power spectrum which is more accurate than HM code and halo fit, but we cannot use for a fusion analysis because the prior range in which it is robust and in which it can be used is narrower than what we are considering for the analysis. So we can test our nonlinear modeling against the Euclid emulator 2, but we cannot use it for our fiducial results. We tested HM code 2016 and halo fit and HM Code 2020 against Euclid Emulator 2, and we found that the new version of HM Code 2020, was the most accurate of the three choices. So we decided to use that for our hybrid analysis. And then regarding baryonic feedback, we decided to double down on mitigation methods against baryonic effects. So we decided to use both scale cuts, which is the DS approach, and the free HM Code 2020 parameter, which is equivalent to the KiDS approach. And regarding the sampler, there was a paper that came out from the DS analysis that showed that for 3 times 2 point, polychord produced more accurate constraints, and Multiness had systematic underestimation of the S8 constraints by 10%. So in one of the appendices of this paper, we revisited this by looking at this comparison of samplers again, but for the case of cosmic shear only. And we found the same, we arrived to the same conclusion. So we found that compared to MC sampler, such as MC, polychord was very consistent with MC, but Multinest underestimates the uncertainty by 10 to 30%. And this is already explained in that paper from Pablo Levos and Noah Weberdick. And it's due to the way in which Multiness samples the parameter space using ellipsoids. And somehow, if the posterior distributions are non-Gaussian, it ends up underestimating part of the tail of when the posterior distribution is highly skewed, which is the case for weak lensing. And so this is why we decided to use polychord for the hybrid pipeline.
You explained why you didn't use Euclid Emulator 2 because of prior ranges, but if you're testing against MC, why not just use MC?
So there are two reasons for this. One is that MC is not a nested sampler, so nested samplers are used because they can provide an estimate of the Bayesian evidence, which is used for some tension metrics. And the second reason is that MC does not handle very well parameter space with 20 free parameters that are with non-Gaussianity. So in that case, it takes much longer time to converge than polychord or Multiness, for example, and so it's for practical reasons it's better to use the other one.
But we trust MC to be more correct. Polychord is closer to MC, but maybe they're both wrong and Multiness is right. So why do we trust MC?
MC is a Markov chain Monte Carlo sampler. If it runs for long enough, it will converge to the true posterior distributions. And the other ones, they start at the edges of the prior and then they converge towards it's a different type of sampling.
Once we determined our hybrid pipeline choices using the mocks, we could finally start looking at how things shift on the data. So here we're showing a reanalysis of KiDS and DS data, but separately, we haven't combined them yet, using each other's pipelines. So on the top panel, you have KiDS data, and on the bottom panel, you have DES data. When you use DES pipeline, you're in green, and KiDS pipeline, you're in orange. And like we saw on the mocks, these shifts, these differences in S8 due to our pipeline choices are real on the data. So you can see that whether you use, on the same data, whether you use KiDS pipeline or DES pipeline, you can get S8s that differ by 1 to 2 sigma. And the uncertainty on S8 is by, almost a factor of 2 as well. This validated what we saw on the mocks, or really is a pat on the back that we came up with this hybrid pipeline set of choices, because these differences are appreciable. Now we're turning to the hybrid pipeline results. So I'm adding in those constraints on both plots in pink, and we can start to think about which things were causing what shifts. So looking at the top panel for the KiDS data, let's compare the orange constraint, which is KiDS data in KiDS pipeline, so like their fiducial analysis, and now the updated results in this hybrid pipeline is shown in pink. And what we see is that there's a small shift towards higher values of S8, and the error on S8 is a bit bigger. And we identify, based on our mock analysis, which things were most important. And as Anna said, for the KiDS data, 2 things really stand out. It's the choice of the sampler, so that makes you have a more conservative or more accurate representation of the error. So it gives you a bigger error on S8. And the scale cuts as well, we attributed to causing that small shift towards higher values of S8. And similarly, playing the same game for DES, compared to the DES pipeline results, which is in green, now we get a shift towards higher values of S8 as well, and we get a tighter error bar. So our uncertainty or our model choices gave us a very conservative error bar in the DES pipeline. And the important things here were the nonlinear power spectrum model, so that causes a shift up. So as Anna was saying, we saw that halo fit was not as accurate as the newly released HM Code 2020, which wasn't available at the time. and the intrinsic alignment model as well. So when you move from that complex CAT model to the IA model, you see a shift upwards. And that latter one, each team has shown variance with these kinds of shifts in our fiducial papers, but really it's the combination of them when you add them up. Both sets of data move towards higher values of S8 when you swap to the hybrid pipeline, which was really interesting. So the hybrid pipeline choices cause shifts in S8 by about 1 sigma compared to each survey's fiducial results. And to me, that is a positive takeaway. That is some validation that it is only 1 sigma when we've updated and really scrutinized our model choices.
When I compare KiDS pipe and hybrid for the KiDS data, and then KiDS pipe and hybrid for the DES data, there isn't this kind of hybrid leaking out the higher values, which I guess you were saying is partially due to scale cuts. Did you undo the scale cuts and then go into the nonlinear for the KiDS pipeline, or?
That's a really good point. I think what you're asking is that, and we should clarify this, that for the DES data, when we reanalyze it in KiDS pipeline, one of the main differences, we showed at the start between our KiDS and DES pipelines was that for baryon feedback, KiDS uses this parameter to marginalize over the effects of feedback, whereas DES use scale cuts. Now, when we were analyzing DES with KiDS pipeline here, we did not lift those scale cuts because it's significant levels of work to validate that small scale data vector, and we decided that was beyond the scope of this analysis.
And that's essentially why the pink one on the bottom panel hasn't leaked out, because the scale cuts are already there in the KiDS pipe yellow plot.
Yes, all these 3 analyses have the same scales used for DES. You're just switching on and off a feedback parameter.
So we looked at why the KiDS data or the KiDS results are changing when we do the scale cuts. So one reason could be that it's because of baryon feedback, and because we're removing some of the smaller scales, we're not as impacted by baryon feedback. So when we look at that, we see smaller shifts when we consider the maximum value that we used in our analysis. So it cannot be just from baryon feedback. So the other thing we looked at was to see if the noise realization has an effect. So we looked at mock analysis to check in what percentage of mock analysis we see this kind of shifts or larger, and found that depending on what assumptions we make for baryon feedback, we get something between 14 to 23% of times we get shifts that are this large or even larger. So it could easily be from noise realization or a combination of noise and baryon feedback.
So this slide is kind of summarizing those shifts that we saw in the different pipeline choices, trying to make some takeaways from the results. So we can see that KiDS pipe and DES pipe give different S8 values on the same data by up to 2 sigma. And they give really different values in the uncertainty on S8, almost by a factor of 2. But that kind of makes sense that, as we gain in statistical power, we need to reassess the conservativeness of our analysis choices. And so TES, it makes sense that they had to make more conservative analysis choices to be able to handle the statistical power. The hybrid pipeline choices shift S8 by less than 1 sigma compared to each survey's fiducial results, and that's consistent with what we found in the mock analysis that Anna was talking about. And then the last thing that you can see here when we put the 2 on the same plot is that KiDS and DES data are still consistent within about 1 sigma, so we can go ahead and combine them. So we had a really nice addition from the HSC team, and we were super happy that they were keen to be on board analysis. So shout out to Ruhi Dalal and Jianzhong Li, who kindly, we provided them with our hybrid pipeline choices, and they reanalyzed their data also under the same footing. So in the top, you're seeing their fiducial results in the circles, and in the bottom 2 purple results with the stars, those are the hybrid reanalysis, the hybrid pipeline reanalysis of their results. And you can see that they really don't move very much, and you would think that that was because their analysis choices are quite different. But actually, there are a few subtle changes there that just cancel out. So unlike KiDS pipeline versus DES pipeline, which all go in the same direction, and so they kind of exacerbate the differences. The important changes here for HSCY3 are the nonlinear power spectrum model. So they'll update from their fiducial analysis used HM code 2016, and now we're using HM code 2020. There's the baryon feedback parameter prior. So they used a more conservative prior for baryon feedback compared to what we're using here. And the intrinsic alignment model. So they use, like DES, this TAT intrinsic alignment model, and now we're using NLA. And so those all go in different directions. And in the end, their results are mostly unchanged in our hybrid pipeline. Yeah, but it's really nice to be able to see all 3 surveys results on the same footing.
One reason they don't see a big difference between for the IA, so for intrinsic alignment model, is because they have very wide priors on the redshift distributions. And we know that there is a degeneracy between the redshift distribution, nuisance parameters, and intrinsic alignment parameters. So when you have a very wide prior on one, then you don't have much constraint on the other. And that means that when you change your intrinsic alignment model, you don't get much of a shift. And this is something they already show in their own paper.
Back to the results slide again. Now we understand everything.
All right, so you've seen this slide before, and as Alex said, we analyzed the data separately, and we found that the results from DS and KiDS under the hybrid pipeline are consistent to within 1 sigma. So we can combine them. Aside from looking at the consistency between the two data sets, we looked at the goodness of fit of the model. And we found that our flat lambda CDM model under the hybrid pipeline fits the data from each of the surveys and their combination well. So that's another way we can test if the model is a good model for our data. So now once we combine the data, we get a 2% precision on the value of S8, which is 0.79. And I must say that these values here are coming from the mean of the marginal constraints on S8. If we shift to some other definition, it can change by a little bit. And we do report the other values in the paper as well.
I think someone mentioned this in words, but there was never an explicit slide saying this. But when you combine them, there is sky overlap. Do you want to talk about how you take that into account? Because obviously that's, in principle, shared data.
Yeah, so I talked about it actually on the flowchart slide, and then we kind of briefly looked at the picture. But there is an overlap between one of the KiDS fields into the DES footprint, a few hundred square degrees. And what we do is, when we're running analyses for the joint analysis, we remeasure the DES data vector to be all of the data with that KiDS overlap excised, so taken out. So we have a little bit less DES data to work with. And then we have done some tests, which are described in one of the paper appendices, that test that not having much of a buffer region around that region that the KiDS data is taken out of from the DES footprint, that we don't have any cross covariance terms between those two surveys, or at least that they are small enough not to matter for the joint analysis. And so the covariance matrix that we calculate, the analytical one, just assumes that there are no cross-covariance terms in there.
Keeping that DES data in would have just been too much of a headache to work out.
Yeah, there is a way of approaching that with the mock simulations that you can use to build your covariance, but with the sizes of our surveys, to actually properly do that would take a lot of CPU power.
Okay, so now let's have a closer look at the constraints for S8. So as Anna showed near the start, when we combine KiDS and DES, we get constraints that are 1.7 sigma lower than Planck. Let me walk you through this plot. So the first point is the combined analysis, so our fiducial result. Then the second and third one are our hybrid analysis of DES and KiDS. And then in purple, we have the HSC results. And then at the end, for comparison, we have Planck results. Now, all the cosmic shear analysis here are done with the hybrid setup. And I should note that the DES year 3 result here is not using the shear ratio test, as opposed to what was done in the original analysis of DES. And also for Planck, here we're using only the primary anisotropies, so no CMB lensing. And we are using the same cosmological priors as we do for cosmic shear analysis. So it means that the sum of the neutrinos masses is not constant. So now if you look at this plot, you see that all the points are still on one side of the Planck data point. But we have tensions that are lower than before. So for DES and KiDS, we have 1.7 sigma. If you look at HSC, we have something around 2 sigma. So we've gone from 2 to 3 sigma to maybe 1.5 to 2 sigma. Now we can say, okay, maybe everything is consistent, so we solve tension, it doesn't exist. But at the same time, we're still all on one side of the Planck data point. So we're seeing the same trend we have seen for many years with peak cleansing analysis.
But when you say you're all on one side, essentially you can throw away the green and yellow from this plot now, right? Because the pink is telling you the significance, the combined significance of green and yellow being on one side. Can you not add the purple in? Like, why not? Why have we not got a DES year 3 plus KiDS 1000 plus HSC data point here now?
You can see that there is quite a lot of overlap with HSC, both for KiDS and for DES. So this complicates the analysis. Now, there was a recent paper by people in Rubin who tried to do this, and they had to do some sort of approximation to be able to combine the different surveys. But in principle, you can do the combination, but it's going to be much more involved, as Ami was explaining before. Although we have more consistent results, we're still all finding lower S8 values. And if you think about the scales and redshifts that weak lensing is sensitive to, so that is low redshifts and nonlinear scales, versus the ones that Planck or CMB is sensitive to, which is the opposite of that, so high redshift and linear scales, maybe it's not so surprising that we're seeing these differences.
Yeah, I guess my thought looking at this is that if this was all there was, this had been the first analysis done of the cosmic shear. I don't think people would be talking about an S8 tension, I guess, but it's still the case that other analyses that you haven't put here, like the 3x2 point and other things, are also on the downside. So yeah, I mean, I guess there is still that same trend with all the other data. And yeah, sure, when you did this reanalysis, it didn't end up on top of Planck or above Planck. It is still below. So I guess it's
So in order to find out about the sensitivity of our analysis to some of the choices that we made, we also looked at some variants of the hybrid setup. So here the very top line is showing the fiduciary analysis for comparison. And then the first variant, which is the second line, we're looking at what happens if you fix the sum of the mass of neutrinos to the minimum mass. And you can see that the result shifts a little bit upwards, but that's mainly an effect of projection effects and prior volume. So the results, if you look at the full posterior, doesn't really change. Then we have the more exciting part that we kind of mentioned at the start, and that's what happens if you change the intrinsic alignment modeling. So if you remember, KiDS 1000 used NLA, so nonlinear alignment model, without any redshift dependence. And the year 3 used the TAT, tidal element tidal torquing model. And in our hybrid setup, we chose the NLA plus redshift dependence. Now, if we fix the redshift dependence, we get the first line in the box, so nothing changes. But if we switch to TAT model, which is a model that has more freedom compared to NLA, then we shift our results to lower S8. And this is a shift that is about 1 sigma, so a little bit less than 1 sigma, despite the fact that when we do this, we increase our uncertainty by 35%. And in fact, if we look at the full posterior and look at the maximum of the full posterior distributions, this difference is even larger than 1 sigma. So this is why I mentioned at the start that I find this the most interesting or surprising result.
It's suggesting that there is something in the data that it's fitting better, right? Like some feature that it's seeing. Whether that's a random fluctuation that it's seeing or not, I guess is the question. But there's something that it's modeling that the data has.
Exactly. And then finally, we looked at what happens if we just ignore baryon feedback and assume that everything is dark matter. And as we expected, what we get is a small shift to smaller values. And that's because when you have baryon feedback, it pushes matter out of the centers of galaxy halos.
Maybe we should clarify there for that point that that's just switching off the TAGN. We kind of say it as if it's like the effect of baryonic effects, but you still have significant skill cuts in the data. So that shift is not the impact of baryonic effects.
And if anyone is wondering what that TAGN modeling is, I think Tilman Trista gave a talk on Cosmology Talks a few years ago where we went into detail about that.
So yeah, another aspect of the analysis we really had to think quite a bit about was the model of nonlinear growth. So then those nonlinear contributions to the matter power spectrum that Marika was showing before. And as was introduced before, we modeled this signal using HM code 2020. Unlike with some other aspects of the analysis, like baryons and intrinsic alignments, there was actually a fairly clear-cut answer to which of the tools available to us was the best choice in this case. So that's what the little panel in this plot shows. We've taken one particular bin pair from our joint data vector. So this is the psi minus part of the data vector. And we're showing the deviations of our predictions from HaloFit HM code 2020 compared with the Euclid emulator, which again we're taking as our ground truth. And as you can see here, HM code 2020 performs basically better across all scales, and this translates to other parts of the data vector the same, pretty much the same. So HaloFit does quite a bit worse. But as you can also see here, HM code 2020 is not perfect. The agreement is not exact. And so although what we've done here is sufficient for now, obviously as data sets become more constraining and become larger, these residual errors will become more important. And so this is not a clearly solved issue. We're going to have to revisit the accuracy of our codes again in future.
And the solution isn't just to use an emulator like Euclid emulator that's just valid over a wider range? Or do you want to have some sort of kind of analytic theoretical understanding of what's going into your likelihood?
Using an emulator is certainly an option if we have one which is accurate and works overall a wide enough parameter space. But unfortunately, I don't think we have one of those available to us at the moment. Another aspect of the analysis, which we took quite a bit of time on, was how we properly account for baryon feedback. As has been mentioned before, we doubled up on our mitigation strategy for this. We applied both scale cuts, both to the DS and the KiDS part of the data vector, and we marginalized over this extra baryon feedback parameter. And there's some residual uncertainty here because HMCode captures baryonic effects which look like the Bahamas simulations. Basically, it's tuned to look like these Bahamas simulations. And the Bahamas simulations, it's a suite of simulations, so it encapsulates a range of severities of feedback scenarios. And we set our prior to basically expand this range of these Bahamas simulations. But we are basically still fixed. We have the shape of the suppression in K looks basically like Bahamas, and you don't have that much flexibility to change that within this model. The scale cuts, to some extent, mitigates this residual uncertainty by reducing degeneracy between S8 and TAGN. So you see that in this panel here. The TAGN parameter is more or less unconstrained by our joint data, and there's some slope, there's some degeneracy with S8, but it's fairly shallow. It's not that extreme.
Out of curiosity, I guess maybe the answer to my question is you were looking to do stuff that was some hybrid of what you'd already done in the relatively distant past, but there are these kind of baryonification models that have come out more recently, perhaps. And in fact, a recent cosmology talk with Giovanni Errico was on Baco EMU. Is the reason you're not using them because of this, you wanted to have a hybrid thing, or is there a reason why you prefer this particular model to those ones? Because I guess they have more freedom than just matching Bahamas. In principle, they have enough freedom to match other types of possible baryonic feedback. I guess what's in the back of my mind is, what if the universe is not captured by Bahamas? Then this model is not capturing the universe, whereas their one has more freedom. So if the universe is different to Bahamas, it does capture the universe.
Yeah, I don't think there's a reason we strongly prefer TAGN or over any other alternatives. The reason we chose this was mostly a practical one, because it was available and it was ready to use. It had been shown to work before. Yeah, so we come to this slide, which is more forward-focused and looking at lessons we can learn and what to draw from analysis. And the top-level thing, I suppose, is that as we gain in statistical power, like as we went from KiDS and DES separately to this joint analysis, we increasingly have to think really deeply and hardly about systematics, and we have to start considering ones that we sources of error that we assumed would previously were negligible. Two of the big ones, like I highlighted on the previous two slides, were three of the big ones: the nonlinear structure formation, intrinsic alignment, and baryon mitigation. For the first part of those, for nonlinear structure formation, it's important to look to start to develop new analytic models along the lines of HMCode and HoloFit, which do better than the ones we have already, and similarly to try and develop new methods for marginalizing over the uncertainties in those models. Secondly, we touched on this a little bit before, but more accurate emulators covering a wider range of parameter space for any variations on priors and models we want to use. And thirdly, linked to that, newer, larger simulations to train those emulators and to validate our models. And for the IA and baryon mitigation parts of this, choices are currently very impactful, and the modeling choices we made here are somewhat subjective. So we don't currently have all of the information we need to make a right decision here. So the areas to focus on, again, more sophisticated models, a better theoretical understanding of these effects. Also, new direct measurements and database constraints. So that's things like using spectroscopic measurements to try and understand intrinsic alignments, or using, for example, SZ measurements to try and constrain the impact of baryons on the matter power spectrum. Thirdly, it's really important to develop more realistic and larger hydrodynamic simulations, because this is a really valuable tool for learning about both these effects, IAs and baryons. And in this area, currently we're somewhat limited by the high simulated data sets available to us. And finally, properly develop techniques where we split our data into separate populations where we think we understand properly the impact of intrinsic alignments. For example, you do a color split into red and blue galaxies and try and model those parts separately.
This intrinsic alignment thing seems like one of the most interesting things, because depending on your prior biases, you would tell two different stories. One would be, lambda CDM is probably correct, so the TATTU is just seeing noise, and it's interesting that now when we've moved to NLA, the tension's gotten less, okay, blah, 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 we're converging on lambda CDM. But on the other hand, it sees something in the data, and so if your prior desire is to see lambda CDM broken, then it's, you could be saying, hey, look, no, there's some physical effect that we're not seeing with the NLA model, and that even if TATT isn't the correct intrinsic alignment model, it is somehow parameterizing something real, and that real thing pulls S8 down, and therefore the tension is bigger. So that looks like an exciting path.
I guess more and more we realize that we can't just keep pretending our galaxies are things that just are ellipses. We need to understand how they interact with each other and what impact they have on the matter-power spectrum. That I escaped galaxy formation.
Simon, you mentioned that spectroscopic surveys will help with intrinsic alignment. Is there like a 1 or 2 sentence way you can just explain that? Because that didn't seem completely obvious. If they were intrinsically aligned or cosmically sheared aligned, how do you know with a spectroscopic survey the difference?
So intrinsic alignment, it's fundamentally a local effect. You get galaxies which are aligning because they're close to these dark matter overdensities. And if you have spectra, you can place where galaxies are along the line of sight. You can separate out this lensing effect and this intrinsic alignment effect.
I see. So for ones that are close to each other, you can't separate the intrinsic alignment and cosmic shear, but for ones that are far enough apart, you would know that if they're similar, that it must be cosmic shear and not intrinsic alignment. Is that a fair?
I think that's fair, yeah.
What work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
We've only analysed the model level of our data, and really at the heart of lensing, calibrating these data sets, the redshifts and the shears. So I think my answer is definitely that under the hood work to be able to produce these beautiful catalogues that we use.
Yeah, to add to that, I think it's very much along the same lines of what Alex said, but in addition to the catalog part, there's a lot of work also for the modeling part, but specifically things like, we mentioned the emulators and other tools like simulation tools or models that are built on tools to be flexible for use in these cosmological analyses. All of that work is particularly valuable to a broad range of people, and then it's also very painstaking work and is also very important.
Hello, me from the future here. You might have noticed there was another author on the paper who wasn't there in the recording. That was Catherine Haymans. She recorded something separately to play now after the recording. In her recording, it'll be clear why she wasn't able to make the main recording, but her thoughts are interesting and wise and give a nice perspective on the analysis and where it leads to in the future. So take it away, Catherine.
Hi, so I thought I'd join you to talk a little bit about the background behind this project. Now, the international weak lensing community have been collaborating with each other for over 20 years now. It all started off with those first cosmic shear teams back in 2000 coming together to do a blind analysis of image simulations, and we all went into the project thinking we were doing everything perfectly, and we all came out of the project realizing that we weren't, but learned a huge amount from each other along the way, and that collaboration has continued across the decades. But competition is also really important as well. We've all got an inner perfectionist inside us, and there are so many different things that we have to do in a cosmic shear analysis. There is always a way that you can do better, always. And at some point you have to stop and you have to say this is good enough for the statistical noise that we have right now. There is immense value when independent teams find the same answer to the same question. But there's also a lot of value when independent teams decide to take different routes to come up with that answer. And that's kind of what we've got with the KiDS and DES surveys. We were both carrying out a cosmic shear analysis, but the approach that we took to reach the answer, what's interesting at the moment is the value of S8, we took different routes. Now, both teams spent an awful lot of time ensuring that those routes that they'd chosen were robust. And they found if they changed the different analysis, then they would find very small changes in S8. So our original plan with this project was that we'd analyse DES with the KiDS pipeline, we analyse KiDS with the DES pipeline, do a joint analysis with both results and publish it. We thought it would take us 3 months. I thought it would be a very short letter. How wrong we were. It was Alex Amon who pointed out to me right at the start, you do know that the analysis choices that we've taken push us in different directions. And the first test that we did with MOX showed exactly that. There are some data sets that you can analyse where the S8 results from the DES pipeline and the KiDS pipeline differ by 2 sigma. And when we saw that in detail, we realised that we needed to do better. We needed to take on new knowledge that had come about since those decisions were originally taken by the KiDS and DES teams, because research changes really quickly and we know more now than we did when those choices were first made. that's how we came up with the hybrid pipeline. And huge compliments to the teams on both sides. Both spent a lot of time choosing their analysis framework in the first place, and so it's hard to say, okay, well, actually we need to improve, we need to do better, but everyone was really keen to do that, and that's the beauty of research. We're always striving to improve. Going forwards, I think there is a lot to learn for Euclid and LSST. One of the things that I would recommend right now is that the two communities come up with a common framework, so we can instantly compare the analyses when they come out from these really new exciting data sets. I would also love to see the same sort of work that we've been doing as a team on the 2-point statistics to cosmology, that same joint collaboration now looking at creating image simulations, calibrating photometric redshifts, shape measurement. We didn't do any of those steps of the cosmic shear pipeline, but as ever, there are always ways that we can improve and learn from each other. And it's been really key to actually work with each other. We've learned so much more by talking than we could have done by just reading the literature on both sides. Okay, I'm going to stop there, but just with a final big thanks to Alex, Marika, Army, Anna and Simon. So for those who don't know, I'm one of the many millions missing from the world at the moment because of long COVID. Before I caught COVID more than a year ago now, we had been working very closely as a team, meeting twice a week, talking through everything. And unfortunately, this illness means I can no longer have multi-voice conversations. It's very strange what it does to your brain, and I need to rest a lot. And this team was just fantastic in accommodating my new disability. I can't thank them enough for how they've pivoted to work in a way that works for me rather than what's necessarily the best way for them to work. So thank you to all of them. And for the rest of you, if you have long COVID colleagues, we can still work, but maybe in a different way than we used to. This project's really kept me sane. So huge thanks to my teammates in Des and KiDS. All right.
Thanks everyone for watching. If you like this, please do subscribe and click the bell to be notified of new videos, and click like to help with YouTube algorithms, both for the channel and for yourself, because YouTube will know to recommend more stuff like this to you. And share the channel with colleagues. There will be a follow-up live discussion or mini workshop of this in a few weeks. There's a link to the Cosmology Talks mailing list that you can sign up to in the description to find out more details about that once they're known. If you want to check out similar talks, I think I might link to a playlist on all things kind of cosmic shear that I'll make, that you can check them out. There'll be talks by Marika, Alex, other Des, other KiDS people. And yeah, other than that, thanks everyone for the great talk and for doing this tour de force of combining the data from two, I guess, similar but different data sets.
Yeah, thank you.